Welcome, everybody. So today's colloquium speaker is Olivier Lai. He's at the University of Nice. Is that right?
Côte d'Azur. Yes.
Okay. He is well known to many of us here for having spent almost 3 decades, 2.5 decades in Hawaii and the Big Island, working at a number of observatories. So he did his dissertation with Pueo on CFHT. So the first AO system on the mountain. So the Rodiers, sorry, being at the University of Hawaii, I should have known that. The first facility AO system on the mountain was at CFHT. And then after his dissertation, he came and was at Keck, CFHT, Gemini, Subaru. Did I miss any?
No, not good.
Okay, the big ones. And now he's back in France. And he's here today to tell us about the next big thing, intensity interferometry. So take it away.
Yeah, thanks, Mark.
Well,
Yes, so
about the question, asking questions.
Oh, I'll do it. Yeah.
Later.
Go for it.
okay, so thank you for the introduction. Hello, everybody. And so yes, today I am here to talk to you about something different, using quantum optics to measure astrophysical degeneracy in Sirius B. So this is a proposal for kilometric baseline optical intensity interferometry on Maunakea, and I call this project OHANA NUI, and I hope the name will become apparent as the talk goes on. So in the next 45-50 minutes or so, I will first describe our previous attempts to do interferometry on Maunakea in the OHANA project. I will describe some of the successes and some of the difficulties that we encountered and how that project eventually came to an end in 2012. I will then introduce the Henry Brown and Twist correlations that allow intensity interferometry. This technique has had a revival over the last 15-20 years, and we're currently submitting an ERC, a European Research Council proposal, and so this is kind of a new version of our old OHANA project. And finally, I will bring it all together with a radical scientific goal, which is the measurement of the diameter of Sirius B. So the OHANA project was a very ambitious project, which basically rests on 2 technological advances that occurred in the 80s and 90s, which were development of infrared single mode fibers and adaptive optics. Single mode infrared fibers allow to propagate light through a fiber while preserving the phase, but they only propagate coherent light. And so adaptive optics is required to restore the coherence of the light after being collected by the telescope to be injected in the single mode fiber. By the mid-90s, this had achieved a certain level of reliability, and we thought that it would be possible to use these techniques to generate interference fringes between telescopes that were originally not designed to do so. And the original paper exposing this idea was by Jean-Marie Mariotti in 1995. He's the one who actually came up with the OHANA acronym, which stands for the Optical Hawaiian Array for Nanoradian Astronomy. In K-band over 800-meter baseline, you get about a few nanoradians of resolution. We started the project with Guy Perrin in Jean-Marie's memory. He passed away in 1998. So Guy had been Jean-Marie's grad student, so we thought that this was something that we should try to achieve. So we spent the years of 2000, 2001 just elaborating a plan and trying to see how we would go about it. And the first thing that we wanted to do was attempt to couple starlight into single mode fibers. So the problem here is you have a 4 to 10 meter aperture and you want to bring the light into a 6-micron fiber core. And so we built an injection module, which you see, so the black ring that you see at the top of this picture is Pueo, the CFHT adaptive optics net. And then everything hanging below it is our injection module. So it's pretty complex. It uses multiple off-axis parabolas. It had to be, modular, so it could go from different telescopes with different F ratios, and of course, very high accuracy. You can see in the picture on the right, the fiber bundle dangling from the telescope going off to an infrared camera. And then detecting the light, you can see that we were able to collect about 10 to 20% of the light collected by the telescope as coherent light, fluctuating with the Strehl ratio. But that was sufficient to achieve stability where we would be able to measure fringes. So following this success, we went to Keck in December of 2002. You can see the injection module next to the Keck adaptive optic Naismith at Naismith. It's basically the optical breadboard, and then the infrared camera is the blue duo by the side. And then we also did tests at Gemini in July 2003 before the instrument support structure was fully populated. So we had access to the focus there, and we did some tests there. You can also see the fiber bundle just dangling from the telescope. So that was pretty successful. We were pretty happy. And so then we thought, well, let's do the next thing on the agenda, which is get fringes using single mode fibers. And I remember showing this picture back then as, you know, so we just put fibers at the focus of the telescopes, bring them down to the, you know, beam combining room, and, you know, use the Keck interferometer to do the delay lines and all that. Of course, it was so much more complicated than that, because each Naismith platform had one of these complex injection modules that had to be precisely aligned. We had to route the fibers through the cable wraps and, you know, maintain them against vibration. And then at the beam combining room, we also had these outjection modules that had to send the light down the delay lines very accurately. So this was more of an experiment that this simple picture showed. And so we were ready to go by the end of 2004. So then we had to contend with the weather. That was one of the other issues that we faced with OHANA. We had a night in December 2004 that was lost to weather. Fred Chaffee, the director of the time, took pity on us, gave us a night 2 months later. So we came back in January. That was also lost to weather. And then we thought we'd put more chance on our side by coming back in summer. And we did get fringes through clouds. We were not able to calibrate them because of an archival failure of the the interferometer system at Keck. But, you know, it was a proof of concept. It was a world first, and we're very, very happy with it. You can see the fringes here. The top row shows the raw signals. So there's vibrations that are shown as a big modulation. And then just filtering at the fringe frequency, you can see the fringe pattern, which is very broad. So we assumed that both Kecks were identical, but in fact, the dichroics were not made out of the same glass, which introduced a dispersion difference, hence the large dispersion of the fringes. But we knew this, so we could compensate for it and keep going. So we tried in 2006. It snowed in May and the road was closed. We had to hike up from Subaru. Then in 2007, the humidity came at us at 100% and never came down. August 2008, everybody remembers Hurricane Felicia that came to visit on the night of our observations. And in 2009, we were unlucky. There was an AO failure at the start of the night that prevented us from observing. And as I mentioned a couple of slides ago, every time, you know, this was 2-3 weeks of setting up the injection modules at the Naismith platform. And it was a lot of work for eventually very little results. In 2009, they weren't really competing, but the teams that were using the Keck interferometer got the results that we were after on young stellar objects and AGNs. So it became much harder to argue for more telescope time to Keck. So you could say we're defeated by weather, but defeated, No, at the same time, we thought we would keep going and do the next easiest baseline on the mountain, namely CFHT-Gemini, because it was one of the shortest baseline at 160 meters, and it's aligned north-south, which means that the fringe speed is slower and therefore easier to handle. Of course, this doesn't take into account the fact that Gemini and CFHT are as different telescopes as you could imagine. One is an Altaz 8 meter with a Schack-Hartmann AO system. The other one is a equatorial mount with a curvature system, 3.6 meter in diameter. But, and also here, we did not have a Keck interferometer to make use of. So we actually had to build our own interferometer from scratch. So we started in 2006, and the first thing that happened was that big earthquake that some of you may remember, 6.5. We were down in Puco. We felt it very strongly. And that's just when we started installing the delay line and realizing that we had no provisions for any earthquake control on these rails that had to be aligned extremely precisely, you know, millimeter flat, less than millimeter flat. So that was the first thing that happened. Then in the summer of 2007, we installed our own beam combiner. It was a new form of beam combiner developed by Julien Voilez. And on this picture, actually, what's interesting is that the most critical component is the little gray box that you see in the corner. It looks like mostly spaghetti, but that gray box is the fibered beam combiner, where the beams are, it acts like a beam splitter, but by bringing single mode fibers very close together, the evanescent waves of each fiber means that there is coupling between them. So that was a fibered beam combiner. All the rest is essentially just a big spectrograph. In the winter of 2007, we installed the pipe that is now used by the GRACES instrument that brings the light from Gemini to Espinal spectrograph at CFHT. And then in summer of 2008, we also needed to determine the baseline very accurately, better to a millimeter, the center of rotation, the relative position of the center of rotation of each telescope, so that we would know where to find the fringes once we were actually pointing the telescopes. So to do this, we got the help of the French National Geographic Institute that came out for a week, 3 people, and they did this using theodolites, using a framework inside the domes and then linking the inside to the outside. You can see the work being done outside here. On the right picture, you can also see the GRACES pipe that was originally the OHANA pipe. And with all this, by spring 2010, we got autocollimation fringes, so internal fringes. So our interferometer was on track. And before going to the big telescopes, I really felt strongly that it would be really useful to validate everything using small telescopes, just to get the entire chain, you know, from finding the fringes to being able to track them, to recording them, to calibrating them, to getting a science result out. Just that we knew that the chain worked before going to the big telescopes, because the big telescope time is so valuable. And so to do this, we use small commercially available Celestron telescopes, 8 inches in diameter. Because the diameter was smaller than R0 at the wavelength of observation, which was J-band, we thought we don't need adaptive optics, just a tilt system to stabilize the light on the fiber head. So, you know, simple adaptive optics really. And we built a kind of amateur interferometer. And it was really quite an amazing experience. So here you can see the 2 OHANA-Iki telescopes with their telescope control computer that were all on wheels, and we had to wheel those out at night to set them up to do observations, which was a fantastic experience up on Maunakea in the open. And I'm particularly fond of this picture, which I call 2 interferometers on Maunakea, granted with very different diameters, but anyway. So with OHANA-Iki, we actually obtained fringes on the sky in 2010 on Arcturus. You can see the fringes here with big steps due to vibration, big variations. There's a funny story about this, but I'll save it for later. In each band, we had a different set of fibers, and they were not completely equalized in dispersion. So when we did autocollimation fringes, we found this big dispersion. Really, one of the difficulties that we faced was the vibration level, which was much higher. We did some tests with accelerometers before installing the delay line in the Côte room, and it looked like a very clean environment. But then when we started doing autocollimation fringes, we got these huge vibrations, and we didn't know if it was the delay line or if the fibers were vibrating themselves longitudinally. Now with hindsight, you know, we've come to realize that what we would have had to have would have been metrology through the fibers. We didn't have it at the time, but this would have been required. The OHANA-Iki telescopes were also used for other purposes. They were used for some experiments in nonlinear parametric conversion, where you use crystals to change the light while maintaining the coherence. So we were able to detect 1.6 micron light at 600 nanometers with the phase maintained. And it was really a fantastic tool for our students. We had a lot of students that came through. They were able to get involved in, you know, real hands-on activities related to interferometry, both practice and theory. We had one summer student, Yue Dong, who got the prize of École Polytechnique for finding the fringe by himself while we were at SPIE in 2010 in San Diego. You know, a bunch of students came through and worked on things like baseline determination, putting the pipe between CFHT and Gemini, et cetera, et cetera. So a fantastic experience. And then in 2012, Guy Perrin was co-PI of the gravity instrument on VLT. He was also vice president of Paris Observatory at the time. Julien Voilez left Keck to go to ISO, and my appointment at CFHT was terminated. So the OHANA project essentially came to a halt because of that. And really, the technical issues were that we were fighting vibrations. And the thing to remember is that the level of the atom, you know, the world is soft and squishy and bouncy. So it's quite difficult. But it wasn't all for nothing. The OHANA project had many offshoots. In Chara, they're trying to extend to kilometer baselines with a movable telescope using the same H-band fibers that we were using, not the same, but the same technology and the same people involved. The progress on the fluoride glass fibers that we did in OHANA is what gave Guy the confidence to use these fibers to do the spatial filtering on the VLTI gravity instrument, which led to spectacular results on such a star. And the OHANA-Iki concept evolved through various iterations and is now being presented as a stellum by Xavier Aubois as a 13 telescope, small telescope linked by fibers, so they have an equal internal delay, and then using the VLTI delay lines to do imaging of stellar surfaces. So as I mentioned, OHANA was hard, fighting for stability at the level of a fraction of a wavelength of light was difficult. And we thought we could do it, but it was hard. But then, what if we could have done the same thing, but without delay lines, without worrying about the atmosphere, vibrations, or OPD matching? But the catch being that we would have to learn a new technique, which is quantum optics. And this is where intensity interferometry comes in. So in intensity interferometry, what you're looking at is this correlation function. So you're looking at the intensity of two detectors that are separated both in space by delta R and in time by a time tau, which is obviously very, very small. And you're just looking at the correlation of these two fluxes. That's all you're doing. And so what do you see? The first thing you see is that there is photon noise. It's a shot noise. It's like, raindrops falling in a bucket. It's always there. There's no correlation in that. And that's the case of a perfect laser, which is monochromatic. You just get the shot noise. But if you look at a thermal incoherent light source, there is yet another source of noise, which comes from the fact that your spectrum is not infinitely small. The spectrum has a certain width, and the phase of that spectrum is random. So if you look at the intensity of a finite width spectrum, you see the intensity has a beating, which is not infinitely fast. And so really what we're doing is we're looking at the amplitude modulation due to very close oscillators, close in frequency, that produce beating. And that beating is then related to the width of the spectrum. So narrower the spectrum, the slower the beating is, and vice versa. So that's really what we're doing, is we're just looking at this, what's called a wave noise. And this is how Henry Brown approached this when he was developing this in the 1950s. He came at it from a radio perspective where photons are very low energy, so you have a lot of them, a gazillion of them, and it basically, the light acts like a wave, and that's totally fine. So in this classical interpretation, the idea is that oscillators, as I said, produce a beat frequency, and so there's a neat analogy with surf and ocean waves, but I have some slides at the end if you're interested. But so what that looks like, this is just a very simple simulation where at the top, I have two oscillators with slightly different frequencies and a random phase. And you can see that there are beats and there is a modulation. And at the bottom, I'm just taking a cross section across the bottom. You can see that there's correlation both in time and along the x-axis. And if I now add a third oscillator slightly offset, I have I have increased the spectrum, so I've decreased the correlation time, so the beating is faster on the plot, right? So this is how it's related. Now, this is using spectral frequencies. With spatial frequencies, this is what it looks like. If you look in the top left corner, you can see a 3x3 little array. That is your emitter. It's made out of 9 oscillators that have a randomly varying phase. And if you look in the far field, so here on Earth, it produces intensity variations a little bit like speckles, in fact, which have a certain size, which is related to the size of the object. So you can see in the main picture that two telescopes that are close together are going to see their intensity fluctuate at the same time, whereas two telescopes that are on either side of the mountain will have a lower correlation. And so here you can see the relationship between the frequency content and the intensity in the image plane. And so this is essentially the Van Zedert-Zernike theorem that is used in interferometry that relates the frequency content in one plane to the brightness distribution in the conjugate plane. So this is the classical wave explanation of intensity interferometry, and it is perfectly acceptable for most cases. However, when we detect light, we detect individual quantas. So something has to be quantized. Either there is an underlying continuous wave and we only detect photons when they reach a certain threshold in energy, or light is really quantized in photons. So to try to understand this, we'll have to go back to first year quantum mechanics and think about, I like to approach it from fermions. Fermions and bosons are kind of complementary particles. And fermions, one of the most striking things about them is the Pauli exclusion principle, right? Which says that no two fermions can be in the same energy state. So for example, in the atom, that's why there are shells. The energy levels are quantized, and in the lowest shell, you can only have 2 electrons, one with a spin up, one with a spin down. And then as you populate the higher and higher order shells, you get more and more electrons. So this is kind of responsible for all of chemistry, this Pauli exclusion principle. Excuse the physicist arrogance here. Now, bosons are the complementary particle of that. Their particularity is that they cannot be distinguished. They like to be in the same energy state. The Bose-Einstein statistics actually describes this, that photons will clump together at the same energy state. So is this a classical wave effect, or is it a quantum effect? And so we have to make the difference here between a young slit experiment where a single photon will interfere with itself, right? You can see in the green plots, the fringes are appearing one photon at a time. This is actually due to the Schrödinger equation, which describes the propagation of the wave function, the probability that a photon will land at a certain position on the screen. And so it works also with electrons. It works with single particles. You can see electrons making a fringe pattern on the panel on the left here, because electrons also follow the Schrödinger equation. Now, for intense interferometry, it's slightly different in that we're now looking at a 2-photon effect. So we have 2 detectors detecting 2 photons, or 2 fermions, in fact. And we want to know the probability of them being detected simultaneously. And so let's take the case of fermions first, where we have the blue and red curves, which, if they were true, you would emit 2 entangled particles from a single source, S1, and detect it at D1 and D2 simultaneously. But the Heisenberg uncertainty principle prevents that from happening. So this is where we actually see that with fermions, this has been demonstrated, there's an anti-correlation. When I say the Heisenberg uncertainty principle, I mean that the delta E, delta T, time of arrival, has to be greater than H, the Planck constant. So you cannot have 2 fermions arriving at the 2 detectors at the same time. And this is what's illustrated here on the correlation plot for these matter waves of helium and tritium. Bosons, as I said, are the complementary. So in the case of bosons, you cannot distinguish which one was emitted by which source. So the yellow and green wave functions and arrows up here are indistinguishable. You cannot know if the photon received at D1 was emitted by S1 and S2, if the photon at D2 was emitted by S2 or S1. The 2 are equally probable, and so therefore the probabilities add, and there is a factor 2 quantum mechanically to having that detection occur when the different sources are received by the different detectors. So this is about as far as I'll go with this, but if you're more interested, there's a lot more behind it. Now, Henry Brown used this idea for the first time in 1956 on Sirius A, using 2 1.5 meter telescopes. Actually, as Mark reminded me, they were actually projectors from World War II. And he was able to measure the diameter of Sirius A to about 6.8 milliarc seconds with a baseline of 9 meters, so at short wavelength in the visible. And this was historically remarkable because it was kind of the first stellar diameter measurement since Michelson and Pease had measured Betelgeuse in 1921. So with that success, they decided to build a full-scale interferometer, but they couldn't get funding in the UK, so they went to Australia and built a Narrabri intensity interferometer, which is essentially a circular railroad track, 188 meters in diameter, which allows to do any kind of separation and orientation of the baselines. Using these 2 6.5 meter light collectors, they basically had a photomultiplier tube for photocathode. The prime focus, actually full scale here, you can see a horse and 2 people, so 6.5 meter were pretty big, but the optical quality wasn't very great. All we needed was to get the light on the cathode. And they observed during more than 10 years, and a seminal paper was the angular diameter of 32,000 bright stars that they published, a catalog of stellar diameters of young bright stars, and a variety of other papers. Now, the issue with intense interferometry is the signal to noise, and this is why after Narrabri, intensity essentially stopped. And so to understand the idea of signal to noise, we go back to the idea that when the spectrum is very large, the coherence time is very small. So let's say you're in the visible and you take the entire visible spectrum, 500 nanometers, going from 500 to 1 micron, and you look at the correlation time. Well, the correlation time on such a wide spectrum is essentially the same as the period of one wavelength of light, which is a femtosecond, and no electronic can touch that, right? It's impossible. So what you do is you use a narrow filter. For example, if you use a 1 nanometer narrow filter, the coherence time is about on the order of a picosecond, which gets a little bit closer to what we can do. But of course, we're throwing most of the light outside of that 1 nanometer wave path away. And it's still too fast for the electronics. So if you have an electronic time resolution called tau L here, and your coherence time is tau C, well, you can see that if your electronic coherence time is 100 times longer than the coherence time, then the peak of your coherence is 100 times smaller. So you're spreading out your coherence peak over that longer time frame. So your signal to noise actually goes down because you have to get that peak 100 times smaller than it was. And so so you're trying to measure this coherence peak out of the photon noise, right? I mentioned at the beginning that shot noise was always there and dominant. So what's the signal to noise dependent on? Well, the usual suspects. First of all is the V squared, so how high the coherence peak stands out above the noise level. Then you have the throughput and the number of photons emitted by the source per meter squared per second per hertz, the collecting area, the square root of the observing time, and 1 over the square root of your electronic time resolution. This equation is valid when you're photon noise limited, as I just mentioned, and you can see that in most of our experiments, we fit the photon noise very well with our parameters. Henry Brown was the first one to realize that the way to increase this, you could add a square root of n channels in front of this. If you have multiple independent spectral channels, you can measure them individually and then average them. So intensity interferometry essentially stopped because Antoine Labeyrie in 1974 was able to get direct interference fringes between two telescopes separated by a certain distance. And here the advantage is huge because you're broadband, so you get like a lot of light, a lot of signal to noise ratio, and you can see the fringe pattern in real time. This comes at a huge cost though, which is the precision at which you have to control the optical path difference in each arm of the interferometer. So you need high quality optics, you need adaptive optics, you need delay lines, and you need to track your fringes if you want to be able to integrate them, which has only become possible recently, with the dual feed adaptive optics. And all this obviously gets even worse when you try to use optical fibers for coherent transport, as we found out with OHANA. Nowadays, single mode fibers are used as vibration sensors to detect earthquakes on the seafloor, or to detect traffic. So maybe not the best technology for this. So when choosing between amplitude and intensity interferometry, you have to pick your challenge, right? Amplitude interferometry does the job because it's photon efficient, but it's hard because of the precision, the mechanical and optical precision you need. Intensity interferometry is not as efficient, but because of the electronic precision that sets the kind of the amount of the distance that light travels over, 100 picosecond, which is a few centimeters, anything inside that is blurred. So turbulence doesn't matter, optical quality doesn't matter. And by recording electronically the time of arrival of photons, we can do other things like post-processing. One thing to realize is that since Henry Brown intensity interferometer technology has moved enormously, especially through telecommunications and quantum cryptography and quantum computing. So detectors have gotten amazingly much more sensitive, faster. We now have GPS and atomic clocks and the telecom fibers. The computers also, we can record the arrival time of individual photons over the course of a night. So this has renewed the interest of intensity interferometry over the last, say, 15 years or so, with various groups working on it, with simulations theory, lab experiment. There were successful experiments bunching on the sun, and then successful attempts on stars until about 2019 by these other groups. And this was mostly driven by these high energy astrophysics Cherenkov telescope arrays Here is an example, an artist impression of the one at La Palma, the CTA with the biggest dishes, about 25 meters in diameter. And for these, they cannot use them when the moon's up because they use very sensitive photomultiplier tubes. So half the time they're idle, maybe not half, but a third of the time they're idle. And so this is where they could be used for intensity interferometry. So as I said, since 2019, there's been some success in stellar intensity interferometry using telescope arrays used for Cherenkov. Down at the bottom right, you see the Veritas array, which is made out of 12-meter dishes with 80 and 100-meter baseline kind of rectangle. And they were able to measure, the diameter of a few stars. And so you can see in the picture in the top right, in the background, the hexagonal array, the photomultiplier tubes that are used for the high energy astrophysics. When the moon's up, they bring out the black plate on top, and there's that 45-degree mirror. So the light comes from the left here, is reflected down the photomultiplier tube. It has a pretty large collecting area because the image quality is pretty dreadful. It's about 1 centimeter. And the time resolution is about a nanosecond for these photomultiplier tubes. So, for this, it becomes hard to imagine how you would do spectral multiplexing because you have poor image quality. So, how do you do a spectrograph when you have this bad image quality? How do you separate the wavelengths, etc.? So it seems that for them, the only way forward is to build bigger and bigger telescopes to gain in sensitivity. And you can see down in the bottom, the first prototype of the 25-meter, 23-meter CTA telescope at La Palma. I mean, it's gigantic. The question is, where do you go next, right? Once you have that, you're kind of stuck with your limiting magnitude. You just need to integrate longer. So the other option would be to use optical telescopes and then bring the light to a multimode fiber. And then you can connect it to very fast detectors like these single photon avalanche diodes, the SPADs that have a time resolution of a few hundred picoseconds. We're currently working on the development. I mean, they exist already, but we're trying to adapt them to our needs for intensity interferometry. These superconducting nanowire single photon detectors, SNSPDs, that have a time resolution on the order of 50 picoseconds. And so then it becomes much easier also to disperse the output to do the spectral multiplexing. You can just use a free air propagation spectrograph design, as I kind of grossly illustrate on the right there. But also, if you could go into single mode fibers using photonic lanterns or some interesting photonics technology, then you can do photonic spectrographs there's many options that you can do. I'm just showing one little diagram here, but it offers a lot more ways forward in the future to improve the sensitivity. And that's why we chose this philosophy, is the potential for increased sensitivity. Also because we have access to these 1-meter class telescopes. And so who is this we? Well, our team is a collaboration of 3 groups at the Université Côte d'Azur. One group is our specialists in cold atoms and quantum optics, manipulating single atoms at a time, led by Robin Kayser. Guillaume Labéry is the son of the infamous Antoine Labéry. And then we have the Lagrange laboratory, of which I'm part of, which is the astrophysics branch. And so we're in doing all the science cases and trying to see how to use it. And then we also collaborate with GeoAzur, which is a geophysics department, and they're specialists in lunar ranging using lasers. And so they're very good at time measurement and time distribution. And also we have access to our telescopes near grass. We have 2 1-meter telescopes that are called C2PU. They're on an east-west baseline, 15 meters apart. And you can see that with 100 micron fibers and the native focal length, we're pretty well sampled to collect all the light into the multimode fiber. So injection module essentially consists of a guide camera, and then we make the beam collimator to have a narrowband filter, a polarizing beam splitter cube, and then we send the light of the polarizing beam splitter cube to 2 single mode fibers and just detect the light. So you can see in the picture in the bottom right what the injection module looks like. It's very small, very tiny, very simple, reliable, much nicer than what we did with OHANA. And so in 2017, William Guérin published the first paper of this revival doing temporal correlation using a single telescope. And then the next year, finding the bunching peaks with a 15-meter separation on bright stars, granted, Rigel and Vega, they're 0 magnitude stars and require about half a night to a night of integration to get that kind of signal to noise ratio. But it was a proof of concept. So we were able to infer the diameter from these visibility points, and you can compare them to known or measured by other methods, interferometric methods, stellar diameters, and we're well within error bars. Since then, we've published 3 more scientific papers, essentially on the distance to LBV stars and P Cygni. The last one was actually on the H-alpha envelope of gamma cats, which has been observed interferometrically many times by Chara and I2T. But the reason I bring it up is because to do this, we use the MEO telescope, which is a lunar ranging telescope. You can see our injection module in the picture bottom left at the bent Naismith focus, I guess you'd call it. And of course, here the image rotates. So we mount our injection module on a rotator. It's pretty simple. It just rotates with the telescope. And then what's cool is that we use the T1M, the Télescope en mètre mobile, which was built by David Vernet, who is a professional optician at Nice Observatory and polishes mirrors by hand. And so you can see him pulling it out of his trailer there and assembling it. And then at night observing, you can see our injection module at the Newtonian focus. It's a Dobsonian mount. And with this, so we were able to obtain these visibility points. And you can see actually on the visibility map that we had 2 baselines. We had a long baseline, the outer circle, and then a shorter baseline. So we were able to move the portable telescope to cover the UV planes. We also have improved the injection module slightly. It now has a tip-tilt plate that you can see up in the front on the top right picture. And we also split the output of each polarization into 2 separate detectors. So we get the 0 baseline calibration for free, essentially. And anyway, yes, the modeling kind of fits what was observed by Philippe Stave with Chara in 1995. But so anyway, this is the progress that's being done with the array currently. In 2019, we were invited to go to SOAR, and we had a night with the 4-meter telescope. So with a single telescope, obviously, you can't do the spatial correlation, but you can do the temporal correlation. And I'm not going to go into this very much because there's a lot to talk about. But the idea, if you remember, I said that lasers do not show any correlation. So the idea is that you can use this technique to detect laser light or very, very high accuracy spectroscopy, much higher than what you could do with the spectrograph. And the idea is that there are astrophysical lasers, or it's been speculated for the last 30 years or so. And one of the sources is ITACAR. And like I say, I'm not really going to go into all this, but this is the other aspect of our ERC proposal, is the temporal correlations. The reason I'm showing this is because we arrived in the afternoon, set up at the Naismith focus, observed during the night, dismantled the next morning, and we're gone. So it was much, much simpler than our previous OHANA attempts. In the same vein, we also are doing experiments with the auxiliary telescopes at VLTI, where, when they use the large telescopes, the delay lines are all being used. So the auxiliary telescopes are essentially idle. And so we don't need delay lines because we can introduce the delay temporally. So we put our injection module minus the tip tilt that we don't need because the ATs have adaptive optics with a beam splitter to collect the visible light. And we were able, with a 49-meter baseline last year, to measure the decrease in coherence, so the V squared for a 49-meter baseline on Spica. And you can see that all the equipment fit in 3 suitcases. So again, orders of magnitude simpler than our previous OHANA project. In fact, we're going back to VLTI early next month for 5 nights of observing with 3 telescopes this time. So we've demonstrated that we can do 3 telescope correlations. We did this in Nice with bad weather, but you can see the flux being injected in and counted here. So that is our next step. So why am I telling you all this? Well, our postdoc, Nolan, realized that if we had spectral multiplexing and these SNSPDs, we would be able to get enough signal-to-noise ratio on Sirius B in about a month of observing with our 1-meter class telescope. At the Calais Observatory, it's a plateau, so we have a movable telescope. So we thought, well, we could do a kilometer baseline, but it would be serious observing. A month of observing, we'd need probably volunteers to help us, etc. But then we also realized that if we had access to 8-meter class telescopes, this could be done in a few nights of observing. So the idea didn't fall on deaf ears. So why would we observe Sirius B? Okay, so Sirius B, the first thing that I like to mention is the historical connection to Sirius A, which was observed by Henry Brown and Twist 70 years ago. So there's a kind of a nice historical connection to observe its companion with the same technique, but 10 magnitudes fainter. And so then what would we learn? Well, white dwarfs, though well-known, are very exotic objects. They're usually produced when the nuclear fusion stops inside the core of a star and the shells are ejected into a planetary nebula. And the core of the star that remains is mostly, it's held up. There's no energy being produced. So it's held up by electron degeneracy. The electron forms a gas. And because electrons are fermions, that you can have no two electrons in the same energy state. So they fill up the energy levels in this gas, in the core of the gas, it becomes degenerate. And it prevents the gravity from collapsing the star further. So the temperature of white dwarfs after they've ejected their shell is about 100,000 K, and then they slowly cool down over the eons. But the temperature at the core, the temperature of the degenerate electron gas is much, much higher. So white dwarfs are pretty strange stars. One of the things that's strange about them is the more massive they are, the smaller they are. You know, most objects in the universe, the bigger they are, the heavier they are. And so to kind of get a feel for what they are, they're about the size of the Earth, but the mass of the sun. So they're about 200,000 times as dense as the Earth. There's an upper limit to white dwarfs, which is called the Chandrasekhar limit, above which they turn into either neutron stars or black holes. The atmosphere is very interesting. In the atmosphere, all the heavy elements, because the gravity is so strong, fall on the crust of the star. And all that's left in the atmosphere is hydrogen, pure hydrogen, and helium. And the atmosphere, you know, as I mentioned, if a white dwarf is the size of the Earth, the atmosphere would be about as tall as a skyscraper. And the core itself is made mostly of oxygen and carbon. So there's been this idea that maybe under huge pressure, they actually form diamonds. They've been, you know, colloquially called diamond stars, but this is something that people are actually seriously investigating. And eventually, as I said, they just cool down. And the idea is that once they've emitted all their energy, they turn into black dwarfs. There is no known black dwarf in the universe. The coolest known white dwarf is about a few thousand K. And this argument was used by Wingett et al. In 1987 to provide an estimate of the age of the universe to 10.3 plus or minus 2.2 gigayears, which is not bad considering. I always thought there was a circular argument here, because if a black dwarf doesn't emit light, how could you detect it? But this is not my my area of expertise. So why measure the radius of a white dwarf? Well, there is a well-known equation of state, both relativistic and non-relativistic, which I'm showing here, which shows this inverse relationship between the mass and radius. So the more massive, the smaller the radius. And when you can see on the plots here that most known white dwarfs fall very accurately on these kind of equation of state parameter lines, adjusting for temperature. The difficulty is how do you get these parameters of mass and radius? So mass can be obtained either dynamically in binary systems. You can get it also from other stellar parameters. The diameter is always gotten from the luminosity. And if you know the luminosity and the temperature, you know essentially the size of the emitter normalized to the distance. It's the R over D parameter, but if you assume you know the distance, you can know the size pretty well. So you can see, for example, in this plot in the bottom right by Basto et al., that the main uncertainty is on the mass. The radius is pretty tightly determined, right? But there is a slight discrepancy in the mass-radius relationship. This is on Sirius B, in fact. The red points are obtained from the atmosphere. You get the mass of the white dwarf from the atmosphere, from the log G. And the blue points on the right are from the gravitational redshift of the hydrogen lines that are being emitted from the atmosphere. And in both cases, again, the discrepancy comes from the mass, but you can adjust it by adjusting the radius. So providing an estimate, an accurate estimate of the radius, will be an extra data point to try to resolve this mass discrepancy, this mass radius discrepancy. So what about signal to noise? Well, we know the spectrum of Sirius B rather well. So we pick a wavelength where we know our fibers transmit well, but the flux is still pretty high. So about 440 nanometers, we could go shorter, but then the fibers don't work as well. We make some reasonable assumptions, throughput of 10%, V squared of 0.7, and we find that with 2 8-meter, with our current technology, so if we just take our injection modules that we have in NICE right now and were to put them on, you know, Gemini and Subaru, in one night, we would get a signal to noise ratio of about 2.4. So we would probably see a bunching, but, you know, marginally. It would be a neat demonstration, and it's kind of comforting to know that we could do it with the current technology. We can only go up from here. So if we had spectral multiplexing, so say the SNSPDs with 16 spectral channels, with 2 8-meter telescopes in a full night, we'd get a signal to noise ratio of 10, which gets much more interesting. If we can get 500 spectral channels, at the expense of a little bit of electronic time resolution, we would get that same simultaneous ratio of about 10 in an hour. And that's really where we want to be, because the projected baseline moves on an east-west baseline like Gemini Subaru. So you want to be able to cut out this projected baseline pretty accurately. So this is really where we want to be. And that's what we're aiming for. And so, going back to our old OHANA ideas of making baselines on the summit, you can see that the longest baselines are essentially between Subaru and CFHT at about 800 meters. So if you take a wavelength of 440 nanometers, the first zero of the visibility function is at 120 micro arc seconds. So if the object we're trying to observe is 40 micro arc seconds, we're about 2/3 in of the visibility curve, where it's about 70%. 70% is ideal because it's still a high correlation peak, so good signal to noise ratio, but it's sufficiently different from 1 that we can fit a uniform disk model with high accuracy. So this is kind of ideal. And on top of that, the time to observe is now, well, within 10 years, let's say, because the aphelion of Sirius B is in 2025. And it's going to be at 11 arc seconds. It's currently almost at 11 arc seconds. But this is kind of important because the delta mag is about 10. So you want to avoid as much contamination as possible from Sirius A. So, but we have a window until about 2035, maybe, where we should be, we can do this really well. I point out here that adaptive optics is actually not necessary because you're outside of the ring of influence of the actuators, in the AOPSF, but it can't hurt because you're putting the flux of Sirius B more tightly into your fibers. So that helps. So to do the spectral multiplexing on Maunakea, we still have to demonstrate a few technologies. So the first one is the photon tagging. So currently we connect the APD to this time digital converter, the TDC, and they're connected by BNC. So we have a single correlator that does the correlation. However, these correlators are capable of writing to disks. So the idea that we have would be to put one correlator at each telescope and write to disk. And they exist. And I did a small calculation of the kind of data rate that we're talking about. At maximum, we'd get about 15 terabytes per night, which is doable. But on a magnitude 8 like Sirius, on an 8 meter, we expect about 200,000 counts, so less than 100 gigabytes per night. I point out that this is per spectral channel, though. So if we have 500 spectral channels, it's a different matter. So then we have a TDC at each telescope, and they need to be synced once in a while. And we would like to have minimal impact on Maunakea, so we would like to do this wirelessly. So we looked at GPS solutions. They provide about a nanosecond, which is not enough for us. There is another GPS technique called GPS PPP, which allows to go down, but it's very difficult to implement, and it's not very practical. So other solutions require a link with optical communication fiber. It's called White Rabbit. It was developed at CERN, and the idea is that you get, picosecond or tens of picosecond accuracy through a local area network, a LAN network. So this is one of the things that we're exploring is it possible to do this on top of Maunakea? If it is, then there are commercial solutions available that give us, 17 picoseconds over 2 kilometers of fibers. So those solutions exist. And then the final technology that needs to be validated is the spectral multiplexing. Here, the real issue will be the detectors. I think the spectrograph shouldn't be too challenging. I prefer photonics, but we can always fall back on a very conventional air propagation design spectrograph. So we're going to test the new SNSPD detector that decreases the electronic correlation time to 50 picoseconds this summer. And they can be made in arrays of up to 16 pixels. There's a company currently in Switzerland that develops SPAD arrays with up to 500 pixels. In the picture, you see here an array with a 23 pixels, excellent jitter, less than 120 picoseconds for each readout. So, the technology is moving forward, and our collaborators working in quantum optics are on this and know exactly what's going on. So once we've observed Sirius B, right, what do we do next? So we could observe different white dwarfs. The next closest one is 40 Eridani B, which is twice as far away, therefore twice as small. It means that we would need either a 2 kilometer baseline or work at a higher point on the visibility curve, or we just get bigger baseline with a Subaru Keck Gemini CFHT-TMT. If we get past magnitude 12 in limiting magnitude, then we can start doing extragalactic stuff, which gets really interesting too. NGC 4151 is one of my favorite examples. It was observed by Mark Swain with a Keck interferometer with an 85-meter baseline at 2 microns. And what they found is that about more than 90% of the flux was unresolved in a core of 100 microarcseconds. So this is ideal for the kind of stuff that we could do. Between the two Kecks and Subaru, in the visible, we would be able to, really constrain the size of a CFHT-1 nucleus, which would be pretty interesting. And I'm just putting this out there because I was amazed by that. They have recently been able to measure at radio wavelengths the size of 3C273 by doing space VLBI. So they did VLBI using a satellite in orbit around the Earth that was linked to the VLBI array on the Earth. And so the size they estimate to 26 microarcseconds, which is again in the realm of what we're talking about. So if we could get to magnitude 12, that would be another source that we should definitely attempt. So I will now conclude by saying that we're proposing to collaboratively attempt this measurement of the diameter of Sirius B, the closest known white dwarf. Its expected diameter is about 40 microarcseconds, and so there's this historical connection to the first observations in intense interferometry by Henry Brown 70 years ago. Sounds a little bit pompous, ushering a new era of quantum optics, but quantum astrophysics. But it is kind of cool to use a quantum phenomenon to observe a quantum degenerate object. We need to validate a few technical aspects, but I'm very confident that they're well within the current reach and expertise of our team and the technology around us. I mentioned it would be marginally possible to do with the current technology in a single night, but we think that it's better to actively develop spectral multiplexing and get real good signal-to-noise ratio and make a real astrophysical measurement of this. And so, as I mentioned, we're submitting an ERC proposal in May, and so letters of support from Maunakea Observatories would be invaluable to support our proposal. And with this, I thank you.
Thank you for that very interesting talk. So questions, I'll remind people on Zoom, if you have a question, please turn your camera on and raise your hand so we can see you. Otherwise, we can't see your hand raised. And tradition is to start off the questions with the student. So any students have a question? Ian.
I have a kind of crazy pie in the sky question. So could you imagine some sort of complementary working with like Lisa with like a space interferometer where they were both pointed at the same source and they're you have a coherent link between them and their relation extremely accurately. Can you imagine a complementary mission like that?
Right. So the question is can we imagine a complementary space-based approach, right, to this? And in fact, yes, I was thinking about this. With so one of the things that intense interferometry is really good at are compact sources with high surface brightness, right? And so thinking about those, I was like, well, what about neutron stars? Wouldn't that be cool? And so the closest neutron star is the Crab Nebula, and so its diameter is expected to be about 10 kilometers, and it's kiloparsecs away. So I did the calculation, and you're down in the I think it's the nano arcsecond range or almost pico arcsecond range. So and so the baseline that you need is 1.4 million kilometers, which of course we can't do on Earth. But using a couple of CubeSats, integrating for a year, I mean it's magnitude 16, but that's fine. And yeah, as you mentioned, if you know the distance between them, or you monitor the distance, even it could change, right, as you go on orbit, and so you get different baselines. Yeah, I mean that would be pretty cool. And CubeSats are within reach of what we know how to do. So yeah, there's lots of ways to dream ahead. I don't think it's a closed topic. There's lots of things that could be done there.
Any other questions in the room or on Zoom?
Last one. You didn't talk in much detail about what sort of fiber optic cables you're using to connect these. Has that been an area of research and been optimized, or does it not matter so much?
So we use multimode fibers in the visible. So basically we look for the ones that have the highest transmission at the wavelength that we're using, and the technology is pretty well understood. Where there is a lot of interest is to go to single mode fibers. And so photonic lanterns, tapered fibers, all those things are under active consideration, because that's where you really gain a lot when you can do photonic spectrographs and really compact devices. And we're really focusing on the visible for the spatial aspect. So there, the fibers are, they've been used for so long that it's a well mastered technology. We are also looking at infrared for the astrophysical laser, the temporal correlation part that I didn't talk about so much. And there, I was amazed. You can now buy off the shelf a spectral multiplexer. You connect, your single mode infrared fiber, and out it comes at different wavelengths in different single mode fibers. So we wouldn't even have to develop, the spectrograph. You could just buy it off the shelf in the infrared. The telecoms have pushed a lot the technology in the infrared, so we're still trying to piggyback on that. But for the spatial interferometry, the visible is still the niche, right? Because, like I said, in the infrared, the amplitude interferometers like gravity and the gravity upgrade, gravity plus, are just phenomenal instrument. The limiting magnitude on gravity in joule feed is a K of 18. We're not there yet. So. But yeah, the technology is really cool, like following the technology on this. Very interesting.
Follow up on that. Can you kind of say a few words on in your last slide, you talked about the different technologies you need to push forward. And can you say what industries are pushing those things? Is it it's not astronomy.
No.
What's pushing that field and developing these technologies?
Quantum cryptography is a big one. It's apparently much bigger than we astronomers realize. There's a lot of money being poured into this, and they need to detect entangled photons. So the time resolution is very, very crucial. The optical telecommunications, maybe not so much, because they're more pushing in the infrared. But it's just amazing how, I guess there's also time of flight applications, so there are a lot of, there's a lot of interest in like being able to detect single photons and know exactly when they arrive. So
okay. Any other questions on Zoom or in Manila? It's fun. Go ahead.
Oh, hi. This is a fascinating talk, all the more because from a completely different angle with Greg Tarley and others, we got to a very similar idea. The problem we wanted to address is, when you have two gravitational lens image of a quasar, you want to measure the redshift drift, and for that you need extremely high resolution spectroscopy. And we proposed time domain intensity interferometry. We called it TIDY, and we were inspired by the same Hamburg-Brown twist experiment. We didn't know, unfortunately, about your work. But I guess tempora would be the same, right, as time domain. So you didn't talk much about it, but I can imagine, because we also wrote a paper about that. So I wonder, how far do you judge is the technology, what you have from actually trying to do that measurement? I guess you wouldn't need the baseline, you would need a big telescope, and you would need to be able to have this very fast. We even put together an experiment here at the IfA, but it was before COVID, and somehow COVID kind of destroyed that. So we are many years late, and that experiment never worked, even though it was put together on a table. But so you're much more ahead than we are. So what is your view about that application?
Yeah, that's very, very interesting. I hadn't thought about that, but it's true. You could do correlations between two different lenses of the same quasar in the same emission line. The fact that you're using emission lines is a great advantage, because you get that much more flux with respect to the continuum. And by tuning the temporal delay, you do get the spectral shift between the two lines. So you get the gravitational redshift that's induced by the two different paths. I had not thought about that. Did you publish something about this? Because this would be a great.
Well, we actually just published, because we collaborated so Greg Tarley is a particle physicist, and then we collaborated with a quantum laser physicist, and we wrote a paper aimed mainly at trying to measure something in atomic physics, just
Okay.
an atomic split, very, very high, similar problem. But we wrote proposals to Keck. We weren't funded so far to get money to put together something that could go on a telescope. But yeah, this is fantastic.
Oh,
it's very interested in this.
Yeah, it's very interesting. I'd be very happy to keep talking about this offline. I just thinking about it off the cuff of my head. One thing I can see that might be an issue is that lensed quasars are pretty faint, and our limiting magnitude is not that great. So we need to think a little bit, but it's definitely something we should talk about because that sounds pretty interesting, very interesting.
Okay, cool. Thank you.
Yeah.
One more question, Ian?
Yeah, just does the correlation improve like linearly or sublinearly or superlinearly, like with more telescopes basically? Like,
yes, okay, I see what you mean. So so the question is, how does the correlation improve, or is it linear or sublinear or whatever, when you add detectors, essentially, or telescopes to your array? So currently, the only way we're thinking of doing the correlations is pairwise. So that just fills a UV plane, but it doesn't help with this SNR on the correlation itself. Well, I guess it does when you do a fit of a model, right? Now, there is interest in looking at the higher moments, like the triple correlation, because that contains information on the phase of the object. But the signal to noise ratio decreases like a cliff when you do the triple correlation. But it is very, very interesting from a theoretical standpoint. In fact, one of the projects that we're also involved in is using a Cherenkov telescope, which is made of all these facets. And we tilt all the facets so that we put a single photon array at each, the focus of each one. And we do intensity interferometry between all of them. So we basically do an imager, because then we have access to the higher order correlations that give us the phase. This was published actually in NRAS, and it's a pretty crazy concept. I have to admit that even I have limits, but it has been published, and theoretically, if you have multiple telescopes, you can get to the higher order moments, which give you the phase and the higher order moments of the visibility function. So, yeah.
All right, let's thank Olivier again for a great talk.